Maybe I'm the smallest one.
Maybe.
Still the smallest.
สลับไหมคะ as I go on
Okay, that'll do. Are you feeling strong?
Yeah.
You are.
Yes, I am.
That's good, because I'd like you to hold that, please. And what number is this?
50.
50. Let's put some zeros on that. So in one hand, would you hold that, please? So what have we got now?
50,000.
And in the other hand, would you hold that, please? How many have you got now?
50 million.
Billion,
50 billion.
billion, trillion.
Trillion.
No? Oh, each one needs to use two hands.
Yeah.
No, you
Okay.
you need a free hand. So what did we get up to? Sorry, I got 50,000 million billion trillion.
We ran out of the word.
So you've got a bicycle. You've got a tricycle. What do you call a thing with four wheels?
The tricycle.
With four wheels.
The tricycle.
It's a quad bike.
What bike?
Quadruple.
Quad bike, yes. Or a quadruped. Quadruped is kind of something. So we have a quadrillion,
Quadrillion.
Quadrillion.
quintillion,
Quintillion. Hexa.
sextillion. That's the most fun one. So 50,000 million, billion, trillion, quadrillion, quintillion, sextillion, septillion.
Septrillion.
Septillion. No, tillion.
Trillion.
Till.
Tillion.
Not tr. Not tr.
Trillion.
Tillion, yes.
Trillion.
So we've got 50 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 zeros. So what does that tell us? It tells us that I can count really fast. Really? Now let's think about it. If I counted one molecule every second since the start of the universe, I would be up to there. Okay, I would have to count 100 million molecules of water every single second for 13 billion years to get up to this number. Yes, that's a lot. So this really tells us that these molecules are unimaginably small because I've got this many in that bottle. So a big round of applause for my volunteers. Thank you very much. Thank you. Don't worry, I'll pick on someone else for the next thing. Now with a bigger audience, I would have got 9 people up for that. So what we've established is that molecules are really, really small. But they have a size and they have a shape. And the size and the shape of the molecules gives everything we see around us the properties that we see. So if it's hard, it's because of the size and the shape of those molecules and how they fit together. If it's soft or bendy, it's the same thing. It's the size and shape of molecules and how they fit together. And you can show this with a simple little demonstration. Now, if you do this at home, please ask the owner of the newspaper first. Okay? So when we make paper, we take some wood or we take some cloth and we mash it up small and break it up into fibers. And those fibers are long and thin. And when paper is made, those long, thin fibers, they're long and thin because the molecules in them are long and thin, those long, thin fibers get brushed out in one direction. Just like I brush my lovely long hair every morning. 100 times, that's why it's so glossy. And what we can do is just tear the paper. And what we see is the paper tears in quite a straight line and quite cleanly. And what that tells me is that I'm tearing along the direction that those fibers have been brushed. If I try and do it this way, it's a very different effect. The paper has a different property in tearing in that direction, and that's because of the size and the shape of those molecules, even though they're really, really, really small. Now, when I was young, a couple of years ago, when I was young, I used to think chemistry was magic. And so I've been practicing a magic trick to put in the show. And let me explain what it is. I take someone from the audience and I stand them over here. And I do some magic passes and poof, they disappear. And then a bit later on, I come over here and I do some magic passes and poof, they reappear. Now, that bit's not a problem. Okay? Making people disappear, I have no problem with that at all. Certainly I can make most of the undergraduates disappear from my lectures after a few lectures. But it's getting people back that is proving difficult. Now, the ones that I have got back haven't actually had all their arms and legs in the right places. So Sue has asked me politely not to do it on any of you. So what I have to do is show you how to start practicing for a trick like this. And what you do is you start with something small. So I have some salt here. And what I'm going to do is make some salt disappear before your very eyes. So let's just, I'll take some salt. You agree there's some salt there? Okay, so we're going to need to watch very closely as I make this disappear before your very eyes.
No way.
Whoa! And it's gone! Thank you! Thank you! Now, of course, I didn't say that I was going to make it go away. I just said it would disappear, and it has disappeared because it's dissolved. We've broken up those salt crystals, and so the particles in the salt crystals have spread out evenly throughout the water now, and what we've got there is salty water. The thing is, I can get those crystals back with their arms and legs in the right place just by leaving the water to evaporate, to turn into a gas and go and rain on somebody else. It's a bit like this. If we take a glass of water, don't drink this, it's not good for you. If we take a glass of water that looks like this, we take some salt that looks like this, we put the salt in the water like that, we've dissolved it, and then we leave the water out. What's going to happen? Well, this is what's going to happen. Those water molecules will evaporate, turn into a gas, and what we have left is just the salt. Now, it turns out that water is very, very good at dissolving stuff. But there are other materials we can use to dissolve things, and one of them is acetone. So anyone who's ever used nail polish remover will know the smell of acetone. And so I'm going to take, now I buy this in the hardware store because it's good for thinning paints and things like that. And if we take a material like this, let's see what happens when we just pop it in our acetone.
Ooh.
And it has dissolved. Right, so we said that molecules have a size and a shape. They take up some space in the world, just like you do. And at the moment, if you were molecules, you would be a solid. Because what you're doing, you're sitting in one place and not moving from that place. You move your arms and legs, a bit like molecules, they vibrate and move around, but not away from your seat. But if I gave you caffeine, Red Bull, donuts, sugar, you might not be so willing to sit still and be a solid. You might want to fill more of the space, and that's exactly what molecules do. And what I've got here is some molecules that I've given some Red Bull and caffeine and donuts in the form of heat. And what I want to show you is that hot water is moving around, taking up more space, and so what happens is that it will float on cold water. So to do this, I've just taken, there's just some food colouring, and what I will do is try to show you that this works. Now, I've coloured the water so you know which is the hot water. And all I have to do for this is to show you that the hot water will float on the cold. Now, how we do this is we take this glass, turn it upside down, and we put it on that glass. Now, of course, I've had to rehearse this and practice it for many years to get it exactly right. And the first time I did it, I made such a mess that we're still cleaning the red spots off our kitchen ceiling. So I'm going to cheat. Okay, I know you know what these are. I generally, when I've got young children in the audience, I have to ask, just in case they've never seen these before. But if you take two of these and you put them like that, there's a hole in the middle. Now, see, there's a hole, my finger's going through the hole. Yes, it's still a hole in the middle, yeah. But if we then offset them, that hole is blocked up just enough so that we can put the hot water on the cold. Turn this around. Okay, so I'm going to tip it up like that. No, I didn't need to turn it around, in fact. And we got a squirt, I think. But what you can see is the hot water is on the top and the cold water is on the bottom, and they're not mixing together. The hot water is indeed floating on the cold water. Now, some of you, I hope, are being skeptical scientists at this point. And you're saying, but it's only a little hole. That's going to happen anyway. So let's do it the other way around. Let's put the cold water on top of the hot water. Line up the holes and see what happens. So you can see it's like smoke coming out of a chimney. That hot water is rising into the upper glass. The cold water must be going somewhere. So that's falling into the lower glass, and we see that those two will slowly become the same colour. And if I manage not to knock them over in the rest of the show, we'll find that those two are the same colour, and these two will remain red at the top and no colour at the bottom. Now, I said at the beginning that we even breathe chemicals, so I should be able to do that with the air around us. So let me get a bag of air. And now, if you do this at home, please ensure that you have a child available to supervise you at all times. And you do have to make sure that you get the right plastic for the bag. Because some plastics, if they get too hot, they will melt. And they will fall, if they get too hot and melt, they will fall in your toaster. If they get too hot and melt and fall in your toaster, they will catch fire. And if they get too hot, fall in your toaster and catch fire, they might burn your house down. We don't want that, do we? So what you're seeing is that the bag looks as though it's being filled up because those molecules are getting hot, they're running around, they're taking up more space, and what we should find is that the air inside the bag will float on the air around the bag.
Woo!
Never coming down.
Yeah, it's never coming down.
Thank you. Now, chemists, I said, like to know what's in the environment around them, what's in a mixture, for example. And the simplest way for a chemist to find out what's in a mixture is a colour change. And I have two examples of a colour change here. I would normally only do one, but because you're special, I've got some butterfly pea tea as well as my normal bog standard British fruit tea. So this is not black tea with fruit in, which I found was the problem the first time I went to Thailand. I said, could you get me some fruit tea? And they did, and said, here's some fruit tea, and it was black tea with some fruit in, which isn't what I needed. So I learned very quickly, and we started using this. What we can see is we have a colour. Now, you can see there's a colour there. And so what I'm going to do is take an alkali. Now, who cleaned their teeth this morning with toothpaste? Or similar? Sue didn't. Well, your toothpaste has an alkali in it because we all have bacteria that live in our mouths. The bacteria eat sugars, produce acids, and that damages our teeth. So I have an alkali just like we have in our toothpaste. And if I add a little bit of alkali to my, you can see I put a bit, my tea was a bit too concentrated for this. Let's dilute it with some water. So you can see that colour has indeed changed. And if I do the same with my butterfly pea, you can see the colour changes too. So these are showing us that the mixtures are now alkaline. They have alkali in them. They're showing us something. So because they're showing us, the scientists have invented this really complicated word. It's called an indicator because it's showing something. Now, if we take the opposite of an alkali, which is an acid, we add some acid to this, you can see that my fruit tea from the UK has turned back to red. Let's see what happens with our butterfly pea from Thailand. It turns a beautiful purpley blue. So that's now showing us, indicating to us that we have an acid mixture. So that's a simple colour change that can tell you whether something is acid or alkaline. Now this is something that I will bring with me, but as you don't have it as something that's usual, it's probably less likely to go down well. So we'll just have to see. So this is milk and magnesia. In the UK you find it in the baby section of the pharmacy, but it's something you can drink if you need to settle your stomach. If you've enjoyed yourself a little too much the night before, this will help a painful stomach. You know what I mean by enjoyed yourself, don't you? Yes, do. I have to be very careful when there are young children in the audience. Now, why is it called milk of magnesia? It's called milk of magnesia because it looks milky. And the reason it looks milky is because, unlike our salt, not everything is dissolved. There's a solid in here. For you scientists in the audience, it's what we call a suspension. And we can ask ourselves, is it an acid or is it an alkaline? So what we do is we add a bit of indicator, and what do we find? Is that an acid or is it an alkaline? It's an alkali. So now my stomach it's green, you see, my stomach is nicely settled. I'm happy, that means I can enjoy myself some more. What we call the hair of the dog. But what you see is, oh, it's hurting again. It's gone acid. The colour's changed. But if we wait a little bit, oh, hang on, it's not as bad as it was. And we get to that, back to that alkaline. And we can keep adding acid, and it will keep turning it back to, keep settling my stomach until I've dissolved all the solid. Because each time I put a little acid in there, I dissolve a bit of the solid until when I take a drink it looks like this, then it's not going to get better again. It's just like using the charge out of a battery. So once you've got to this point, you'd have to charge it up again by taking some more of this. Now it turns out that a lot of our foods that have high colours, these very intense colours, work this way. So you could use red cabbage juice, you could use red grape juice, you could use turmeric, works as well, as the yellow spice turmeric. They have these high colours. But here I have an indicator which doesn't have one of those high colours. What colour would you describe that as? White.
White color.
White, yeah?
White color.
White colour. Fantastic. So we've got white here. Now, let's make up a solution here. Now, what does this solution make you think of? Sorry?
Light brown.
Light brown, but what other liquids look like that?
Beer.
Beer, okay, yeah, I'll take beer. Anything else?
Tea.
Tea.
Cider.
Pea. Pea? Oh, at least you... Well, I was going to say, compared to me, you're well hydrated. Yeah, some people say apple juice, so there are teas that look like this, apple juice, beer, urine, could be anything, and you don't know. So you take it to your friendly local chemist, and one of the things they might do is use this indicator. Now, all I used there was some, the indicator was some starch, some corn flour. So those of you biologists in the audience will have recognized, and those of you who do chemistry in the audience would have recognized that the solution was an iodine solution, and I've just put in some starch. And so we use this in chemistry. We can tell whether iodine is present by adding starch, and in biology you can do it the other way around. You can tell that starch is present by adding iodine. A few drops of that on a cut potato and you'll have the same colour. But we can do some more chemistry with this because vitamin C, we're told vitamin C is good for us because it's an antioxidant. An antioxidant to a chemist is a reducing agent. And what that will do is turn my iodine in here into iodide. And so it's only iodine that makes this colour with this starch. And so if I add my vitamin C, we should see that we lose that colour. Right. It's about halfway through the show. It might be a little more than halfway through the show. So this is when I stop to have a drink. But somebody, when my back was turned, because I had to go out to powder my nose as well before you came, and I think someone snuck in and put skewers through my bottle. So what I would like you to do is make a prediction. I'm going to take the skewers out of the bottle, and I'm going to ask you to be scientists, make a prediction. What's going to happen to the water? Is it going to come out of the holes, or is it going to stay in the bottle? Who says it comes out of the holes? Hands up.
You take the two of them.
Both of them out? Yep. Who says it stays in the bottle? Hands up. Who says I haven't put my hand up yet? Hands up. So you need to make the prediction in the safety and comfort of your own head, but you have to come down on one side of the fence or other. It's either going to come out, squirt out like that, or it's stay in the bottle. Now I'm going to you've made the prediction, I'm going to do the experiment. So we've got one skewer out, and my fingers are over the holes, okay, so that it doesn't come out prematurely. Take the other skewer out, and what do we see?
Ooh, where is?
Now, why is that? You have to remember that we live at the bottom of a sea. Our sea is made up of air, and just like at the bottom of the ocean, where there's lots of water pressing down, there's air pressing down on us, and it's pressing in on this bottle, on those holes, and the bottle is pressing out on the air, and everything's balanced. But if I do this, then indeed the water does come out of the bottle. But actually I do need a drink, because those of you who've done public speaking will know it's nice to have a drink every once in a while. But I'm going to use this as an opportunity to give you another test. I'm going to have to clear these to the side just for a moment, because I need to give you another test. And this test is a test of observation. Because a scientist needs to be able to observe something happening and then report back on what's happened. And they need to be able to report back what they have seen happen, and not what they think might have happened or what they hope happened. It's going to be what's really happened. So I'm going to take a drink. Let's do it this way. Oh, I did need that. And you see I have 3 cups. All I'm going to do is swap these cups over a bit like this, and at the end I'm going, oh sorry, I didn't tell you where the water was. Here, I have left some water here. Okay, so the water is now in this cup. And all I'm going to do is swap these over a bit like this, and at the end I'll ask you where the water is. So is it in this cup?
No.
Is it in this cup?
No.
Is it in this cup?
Yes.
Okay, you've made the prediction. Let's do the experiment. And it's there. So obviously that was relatively slow, relatively easy. So this time I'm going to try and do it a bit faster, all right? So you're going to have to watch very carefully. Okay, you ready? Is it in this one?
No.
Is it in this one?
No.
Is it in this one?
Yes.
Okay, you've made a prediction. Let's do the experiment. Are you sure?
Sure.
Okay. Right. You're obviously pretty good at this. You're all trained scientists. So I'm going to try and switch it up this time and make it really, really difficult. And I'm going to do my very best to fool you. So, are you ready? Is it in this one?
No.
Is it in this one?
No.
Oh, difference of opinion there. Is it in this one?
Yes.
Okay. Make a prediction. Let's do the experiment. Are you sure?
Sure.
Fantastic.
Wow.
So, now, who says the water is not in the middle cup? The water's not in the middle cup because it didn't come out of this one. Logic says it must be in this one or in this one, right? So, who says it's not in this cup? You say it's not in this cup, okay? So let's do the experiment. You better move your camera out. Okay, I need a count of 3. 1, 2, 3. So, who says the water's not in this cup?
No one's saying.
I'm going to pick on you because you didn't come up before.
I have no hair.
That's fine. So I need a count of 3. 1, 2, 3. Oh, stop. 1, 2, 3, and
Where the water?
I'm trying to dry it.
Oh, surprisingly.
so I said the water didn't come out of that cup. Now, as a scientist, you also have to be very careful with language. I didn't say it wasn't still in this cup. Now, this is a product that you find in a supermarket, in a product that you buy, that you need to lock up water in. What product might that be?
Pampers.
Pampers, yes, and some feminine hygiene products, of course. You find, if you ever wondered, if you have adverts where that blue water gets absorbed, it's this stuff doing the absorbing. That can absorb 400 times its own mass of water, and that's something that chemists have made. Now, I'm going to try to convince you that I'm making a new material. Now, for a start, this doesn't always work. This is normally where slime would come in. This doesn't always work, and secondly, it's not very convincing because the alkali that I have is a bit cloudy to start with. If this wasn't cloudy, and I think that's to do with the fact that Norfolk water is very hard, what I'm going to try to do is make a new material by mixing this, which should be colourless and see-through, and with this, which is colourless and see-through. And see if we can make a new material. No, that's not convincing in the slightest, so I'm going to have to work on that one. But again, that's also nice sometimes to have in the show something doesn't work, because it just shows that these things sometimes don't work. Now, that would have been me putting something together to make a new material, but by the way, don't tell the university's authorities that I'm lighting fires in the lecture theatre, because they'll sack me. They don't need much of an excuse these days. One of the other thing that chemists needs to be able to do is take things apart. And so what I have here is some baking soda, which is, you will know, is sodium hydrogen carbonate, and it's a bicarbonate of soda, and the point is it's a carbonate material. And a carbonate material will give off carbon dioxide when you add an acid. Now I have an acid here, I have a solid carbonate, and I have a liquid acid. So is carbon dioxide a solid, liquid, or a gas?
Yes.
It's gas, that's right. So if I add my liquid acid to my solid carbonate, what should I observe? What should I see? Bubbles, yes. We scientists have a fancy word for this. It's called effervescence.
Oh yeah.
Now sometimes you get a young audience, they say, fire, smoke, explosions. So I say to them, look, you're a solid, right? If you were sitting in a bathtub full of water, which is a liquid, and you made a gas, would you see explosions and fire and smoke? And they generally laugh. Anyway, if we add some acid to my bicarbonate, we see there are indeed bubbles. But I said these are bubbles of carbon dioxide. So what I'm going to try to do is convince you of that by pouring myself a glass of carbon dioxide. Now, of course, carbon dioxide is colourless and odourless, and I don't know if there's any in that glass at all. So let's see what happens when we do this.
Oh.
Now, why did that work? That works because carbon dioxide is denser than air. And just like we saw over here, with the cold water being denser than the hot water, the air floats. When we make carbon dioxide in the bottom, the air floats out. And when I pour myself a glass of water, the carbon dioxide settles to the bottom, the air floats out. And we do it again when we do this. And when we get rid of the air from the candle, it can't breathe anymore, so it goes out. Now, there's something else we can take apart. This is called hydrogen peroxide. And you can often get it in your local pharmacy because people use it to change the colour of their hair. I don't need to, it's happening naturally. Now, the thing is, hydrogen peroxide is a poison. It's toxic. The bad news is that we are all producing it in our bodies right now, just by breathing. But don't stop breathing, that's probably a bad idea. What we do have in our bodies are mechanisms where our biology can turn this into water and oxygen. And these things are called enzymes. And again, I did ask Sue whether I could take some blood or just a tiny piece of liver from you to do this with, but she said no for some reason. So I'm going to have to sacrifice some yeast in the name of science, because yeast breathes as well, just like we do. Maybe it doesn't have lungs, but it breathes oxygen, uses oxygen, and it needs to ensure that the hydrogen peroxide doesn't build up in its body either. Now, the yeast, just like we do, will turn this into water and oxygen. Is oxygen a solid, a liquid, or a gas? It's gas, which is very helpful for us breathing it. So just in case we make any, I'm going to put a little washing up liquid in there. And that's so that if we make any bubbles of gas, they'll be captured by the washing up liquid. And now what we do is we tip it. Now I need your powers of observation to see whether we're going to make any bubbles when I tip the yeast into hydrogen peroxide. So, has that produced any bubbles?
Oh.
Oh.
Take this time.
Now this is only 20%. No, it's 20 vol instead of the 100 vol I had in Brunei.
I think his is a bit old as well.
Yeah, well, it's old, but it's 20 volt instead of 100 volt. You can't buy 100 volt in Lloyd's on Nunthank Road.
So if the hydrogen peroxide is stronger,
And fresher, it will go quicker. I did think I was going to have to use a smaller bottle. If I have this strength of hydrogen peroxide, I will use a smaller bottle, because the audience generally loves it when it does
what's it?
this.
It's coming.
Coming out.
That's the bit they like. So a smaller bottle is going to be the thing to use. There we go. But what you couldn't observe, but what I could, because I was holding the bottle, is that that was generating some heat. So that tells me I can generate heat using chemistry. And for this, I'm going to take a fuel and put a little in my bottle here. Now it turns out that a fuel, a liquid fuel, doesn't burn. It's the gas of that fuel that's mixed with oxygen that burns. And so what I'm going to have to do is warm up my bottle here and make sure that the liquid turns into a gas. and then I mix that gas with lots of air. It's what is happening when you drive a petrol engine car along the road. So you've put in petrol at the filling station, and that's liquid. And the car takes that liquid and turns it into a gas, mixes it with air, and then that's where the magic happens in your car. What I'm doing is trying to evaporate all this. Now, because it's the UK and because this room isn't very warm, I have to make sure this is nice. The bottle's nice and warm, so that we get the gas evaporated into the bottle. And when I do this in other countries, it's sometimes a lot easier because everything's warm. And so the first time I did this, when it wasn't in the UK, was in South Africa, and that really went well. South Africa in a hot month. So what I'm doing there is I'm just getting rid of the excess liquid. So we don't want liquid in here, we want gas. I'm just going to warm this just up a little more. And now, because this is sometimes a little difficult to spot, I'm going to help you by taking the lights down. So watch closely.
Don't do that at home.
Do that at home. And in Thailand and Vietnam.
My mother will angry.
So over the years we've decided that these are definitely the bottles to have. You can use thinner walled bottles, but they are one shot. They will, at this point, they will be going, and so you can only use them once. The other thing with this particular demonstration is that if you have time enough to wait, what you can do is collect the water that's being produced, because that reaction, that combustion, burning the fuel, produced water and carbon dioxide. And if you watch closely, I can tip out the water that's condensed already, because as that water is getting cool, it's condensing and turning into a liquid. And if you look, you can see the water that was produced in that reaction. So we've got the last thing to show you. That is how we power our cars. That's how our cars go along the road. And we have to power ourselves. And we do that by eating food like this corn flour. So this is cornstarch. You can do this with a number of other substances, but cornstarch is just very convenient because it doesn't leave much of a mess to clear up. And we use food to power ourselves, so we have to extract the energy. And what I'm going to try to do for you now is do just that, is to extract the energy from this corn flour. And again, we can take the lights down.
Are you okay?
So that is how we power ourselves. That is going on in your bodies right now. Maybe not a big flame like that, but what your bodies are doing is taking the food that you eat and combining it with the oxygen that you breathe in. Turns it into carbon dioxide, which is in the air we breathe out. Turns it into water, which goes out another way. And it turns it into energy. And that's the energy you have to learn lots of things from Sue this week. It's the energy you have to drink lots of tea with Sue this week. And it's the energy you have to give me a huge round of applause. Thank you.